Hello there. So this is the first video of section 1.5. Here we're going to introduce a new type of linear system that we will be looking at quite frequently, and that appears often in applications of linear algebra. I think this will be a slightly shorter section, but I apologize if the section does end up taking the normal amount of time. I guess there's no way of knowing until the videos are recorded. So we'll just get right into it. So a linear system is said to be homogeneous. And so this is the main definition we want to introduce today, or I guess in this video. If it can be written in the form ax equals 0. And so remember, in the previous section, we had discussed how we can take a linear system and instead express it as a matrix equation, ax equals b. But notice here, we're just setting it equal to the 0 vector. And so here A is an m by n matrix. And so since A has m, since A has m rows, 0 will be a vector in Rm. And notice x will be a vector in Rn. So I've actually got an example of what a homogeneous system of equations looks like here. So notice this is just 3 equations, and we're setting each one equal to 0. And so if we wanted to express it in the form ax equals 0, we would just let our matrix A be 3, negative 3, 6, 5, negative 2, 1, negative 4, 4, negative 8. Where here A is just the coefficient matrix for this system. So today I want to discuss how we can find solutions and interpret solutions to this type of linear system. When we're dealing with homogeneous equations, there's only 2 possibilities because we are never not going to get a solution. What that means is that there's always one solution to every single homogeneous equation. And looking at this, it seems a little silly, but the solution to this equation, notice, is just to let each variable equal 0. And if you'll notice, that makes each of these equations equal to 0. That isn't very fun, but it is always a solution. And in fact, I guess because it's sort of cheating in a way, or because it's not very fun, we call it the trivial solution. Where here, x is equal to the 0 vector. And remember, x is just this vector of variables, so this would be a vector of length 3, consisting of x1, x2, and x3. And so this is just stating these 2 things are actually, in the context of this example, stating the exact same thing. And this is always a solution to any homogeneous system. So, every homogeneous system always has the trivial solution. So we'll always find at least one solution. But as we will see, some systems have non-trivial solutions. And so a solution where here x is not equal to the 0 vector is called a non-trivial solution. And so what I specifically want to do in this video is talk about when we get non-trivial solutions, what properties those systems will have, sort of how we can interpret those non-trivial solutions, and then when do we get trivial solutions? Like, when do I have a homogeneous system of equations that only has the trivial solution? And there are some. So I figured we'd start by working through this first example that I put on the board. Just to give myself space, I'm going to erase everything so that we can work through the example, because since we are solving a system, it'll take a little bit of row reducing. So if you want to continue writing on what's on this board, pause the video here. All right, so we want to solve the following system of equations. I'll rewrite the system on the board, and then I will write the augmented matrix. And if you're following along on the worksheet, this is given as the example on the worksheet as well. Solving this is really no different than solving any linear system of equations that we have solved previously. So what I would recommend is actually pausing the video and trying to set up the augmented matrix, do the row reduction, and get the solution to this, and then you can check it with my work. So pause the video here if you want to do that. All right, so I'll set up the augmented matrix for this system. And remember, this is just the coefficient matrix where I add one more column at the end. But this time, it's just going to be a column of all zeros. And so one thing in particular to note about this, notice that any row operations I do with any of these rows, whether it be a row swap, adding rows together, or multiplying a row by some coefficient, I'm always going to have zeros in this last row. So no matter what row operations I do to get an equivalent linear system, each of these equivalent systems is always itself going to be homogeneous. So first thing, I'm going to choose this 3 to be my pivot. So I'm going to clear out the -3 and the 6. And I'll do this simultaneously just to save a little bit of space and time. So notice to clear out the 3, I'm going to do row 1 plus row 2 and replace row 2. So that gives me 0, 3, 0, 0. All right, so now hopefully I get a 0 here. So now I'm doing -2 row 1 plus row 3, replacing row 3. Should be a -9. -2 times -4 is 8. So 8 plus -8 is 0, and then of course I get a 0 there. How nice. All right, so I'm actually, at this point, fairly close to being done, right? So I've cleared out everything below this first pivot entry. Next pivot entry is going to be this 3. So what I'm going to do is do 3 row 2 plus row 3. And that should give me 3, 0, 0, 5, 3, 0, -4, 0, 0, 0, 0, 0. Now I'm going to divide 1/3 times row 2, because now I want to turn all of my leading entries where it's easy into 1s. I'm not turning this 3 into a 1 yet because the other 2 entries in row 1 are not divisible by 3. Now I want to clear out above my leading ones, so I'm going to do -5 row 2 plus row 1 and replace row 1. And now, unfortunately, I'm not going to be able to avoid fractions in this case. So I'm going to do 1/3 row 1. 1, 0, 4/3, 0, 0, 1, 0, 0, 0, 0, 0, 0. Now, I have my matrix in reduced row echelon form. This means I've got sort of a solution to my homogeneous system. So let's remember what system of equations this augmented matrix corresponds to. So this corresponds to the system x1 plus 4/3 x3 equals 0, and x2 equals 0. So how do I interpret this? Well, notice that I'm going to be able to find non-trivial solutions specifically because I have a free variable x3. So remember, a free variable is a variable that does not correspond to a pivot column. And so in a sense, remember, we can think of free variables as being able to be assigned any value we want. So remember, when we were looking at free variables in the past, if our solution had a free variable, that corresponded to the system of equations having an infinite number of solutions. Right? We get this row of all zeros, sort of another way to sometimes tell that. So, in fact, if I'm going to get a non-trivial solution, which, as we'll see in a second, I do get here, I actually get infinitely many non-trivial solutions. So, how do I interpret this and get a non-trivial solution? Well, I just pick some value for x3. That fixes x1. And poor x2's fixed at 0. But that's OK. And so let's say x3 is equal to 3. Well, then x1 should equal -4. x2 should equal 0. And x3 should equal 3. I made a small mistake, albeit I think small enough that I can correct it. When I was row reducing, notice from this step to this step, I forgot a -4 there. So this should be -4/3. And so this should be x1 -4/3. And that would be the only correction. So I do apologize for that. So notice here I had forgotten to write the -4 there. And some of you might have noticed this and were probably yelling at the video telling me, stop, you made a mistake. So this just means that this is the correct augmented matrix, 1, 0, -4/3, not 1, 0, +4/3. And that this is the correct solution. So this would mean if x3 was equal to 3, x1 should be equal to +4. And now that should actually correspond to the solution. And so notice we could actually check each equation, and we would always get 0, specifically because x2 is equal to 0. So how do we find non-trivial solutions to our linear system? Well, if I've got a free variable, I can assign that free variable to be any value I want. And then once we've given all of the free variables values, all we need to do is just fix the rest of the variables. And so notice in particular here, and we will look at one more example of this video where we don't get a non-trivial solution. We're only going to get a non-trivial solution if I have a free variable in my augmented row-reduced echelon form matrix. And so the linear system AX equals 0 has a non-trivial solution if and only if we have at least one free variable. All right. And we will look at more next video how we interpret these and how we can describe all solutions. But I will quickly write down that statement because it is quite important. If and only if the equation has at least, or the system of equations, I should say, And so you could see in the last example why a free variable gives me a non-trivial solution. But now I want to end with an example of why having no free variables will correspond to no trivial solutions. Or no non-trivial solutions. So again, we're going to solve this slightly shorter linear system. So x1 plus 5x2 equals 0, and negative 4x1 plus 2x2 is equal to 0. And again, I recommend you pause the video here, set up the augmented matrix, and solve it for yourself. All right, so the augmented matrix for this linear system should look like this. Hopefully I don't miss any negatives this time. I've actually been fairly lucky, so I think I have about a 90 to 95% success rate with any arithmetic operation I perform. And I have been a little lucky that so far, at least early on row-reducing matrices, for these videos, I haven't made too many mistakes in doing so. I think there have been a couple of videos where I've made, so that video I'd made a, I think, small enough mistake that I was able to, sort of correct it in the video. But there have been a couple where, like, I think I made a mistake really, really early on and just kept row reducing, and I just had to say, okay, I'll just redo the video. But arithmetic is hard. So if I want to row reduce this, I'm going to do 4 row 1 plus row 2. This is because I've chosen 1 to be my first pivot variable. And I want to clear out that negative 4 below it. 4 times 5 is 20, plus 2 is 22. There's a big number there, but I'm not too concerned with it because I can just make that 22 a 1 right off the bat. 1 over 22 times row 2. And I get the following matrix. And last but not least, to put it in reduced row echelon form, I want to do negative 5 row 2 plus row 1, and that's going to replace row 1. And so I get the matrix 1, 0, 0, 0, 1, 0. And so notice I get an equivalent linear system here of x1 equals 0, x2 equals 0. And so notice that here I have no free variable, right? That means in my row-reduced echelon form matrix, all of my variables correspond to leading ones. But remember, when we discussed how to interpret reduced row echelon form matrices, a leading one corresponds to that variable being sort of fixed in place by this last column. But remember, all of our row operations, because every entry in this last column is 0, will leave all of the entries as 0. So if I get here and I have no free variable, every variable is going to be fixed at 0, and that will leave me only the trivial solution. So if I can row reduce and get a free variable, you can find some non-trivial solution. But if you row reduce and get no free variables, that is, every variable corresponds to a leading one or a pivot, then you get only the trivial solution.